Today we will study the potential energy of a spring, in which we should derive expression for potential energy of a spring. First of all, let us take a spring made up of a perfectly elastic material. One end of the spring is rigidly fixed at O and other end is fixed to a block of mass m. This position is equilibrium position of the spring at point L. When the spring is pulled up to point J, the displacement of a spring is R, and due to this displacement, the work done to displace the block L to J is stored in the spring, that is potential energy. But when the spring is released from J, it comes back to L but does not stop at the point equilibrium point L, because due to inertia it comes to point K, which is L K is equal to minus R. Now let us take a position P when the spring is pulled up to point P at a displacement x from point L, means LP is equal to x. When a spring is at P, the restoring force F is developed in the spring due to elasticity So from Hooke's law, F is directly proportional to x. X is increase in length. F is restoring force developed. Thus, F is equal to minus kx. It is equation 1, where this k is constant of proportionality and known as force constant. And sign, negative sign, is indicates that the restoring force is opposite to the increase in length of the spring. Now let us consider a case when a spring is at point P, which is x at a distance x from equilibrium position, which is LP is equal to x. Now, when we pull the spring up to P, then we have to perform some work to increase in length. Now let us consider the spring is increased up to Q, which is infinitesimally a small distance dx equal to PQ is equal to dx. Now work done in displacing the spring from P to Q is equal to d omega is equal to F into dx, force into distance. But from equation 1 we have kx. We have neglected minus because we take kx in magnitude. So substituting F is equal to kx, dw is equal to kx dx. Now we can calculate the work done on the spring on a stretching up to length x. On integrating this equation between limit 0 to x to 0. Now w is equal to 0 integration 0 to x kx dx, k integration 0 to x dx, k x integration of x becomes x square by 2 bracket 0 to x. Now w is equal to k x square by 2 or is equal to half kx square. This is equation 2. And this work done is stored in the spring as potential energy at point P, at this point. Potential energy at P is equal to half kx square. Now when a spring is stretched up to J, then x is equal to R. Then potential energy at position J is equal to half k r square. When we put x is equal to r in this equation, we get potential energy at J half k r square. At point J, the block is raised, so kinetic energy will be 0 because kinetic energy is half mv square. Velocity is 0, so kinetic energy at J is 0. L is equilibrium position of the spring, so x is equal to 0. Therefore potential energy at L is equal to k x square means 0, where here x is 0, so 0 square. Thus potential energy at equilibrium position L is 0. Now the loss in potential energy when system returns J to L is equal to increase in the kinetic energy of the system at L. Thus potential energy at J, potential energy at L, their difference gives loss in potential energy. The loss in potential energy is equal to increase in kinetic energy. Thus half k r square is also equal to increase in potential energy at L. At point K, block is at rest and x is equal to minus r. Then potential energy at K is equal to half k bracket under minus r square. This becomes half kr square because a square of negative number is always positive. Kinetic energy at k is equal to half mv square. At k, block is raised, so its velocity is 0, so half mv square is equal to 0. Now potential energy of the system at p. First we have seen in the picture that p is at a distance x from equilibrium position, and potential energy of the system at p we have calculated in previous phase. The potential energy at p is equal to half k x square. The decrease in potential energy when system is returns from j to p is equal to potential energy at j minus potential energy at p. Potential energy at j is half k r square minus half k x square. This decrease in potential energy is equal to kinetic energy of the system at p. Now if we draw a graph of P and Ke, means potential energy and kinetic energy against displacement, potential energy at equilibrium position is 0 and at extreme position is maximum. Here is maximum and here is maximum. The graph of potential energy versus displacement is this curve, and now graph of kinetic energy to displacement is this curve. Kinetic energy at extreme position is 0, but at equilibrium position is maximum. But the kinetic energy plus potential energy always remains constant, so their graph is a straight line parallel to displacement.